This is a lecture in the module 2. Today we will be discussing the transistor sizing for asymmetric logic circuits. So, basically asymmetric inverters and inverter chains. So, we will first discuss logical effort of asymmetric gates and why is it important in near threshold voltage regime, and then we will discuss inverter chains. There are several applications where nominal voltage or standard nominal voltage or super threshold voltage standard cells are used in near threshold, are operated using supply voltages which can be called near threshold voltage or sub threshold voltage. So, the same same circuit is operated in several voltage domains. For example, in a mobile phone, in the hibernate and active modes, you would be operating the same circuit in different voltage domains. So, the standard cell library might have been sized for super threshold voltage regime, because that is where you want high performance. So, you might have sized them according to those requirements, and you might have kept balanced output rise fall transition times for a super threshold voltage operation. So, it does not mean that at near threshold voltage operation the standard cell library would have balanced output transition times, and the reason for that is that the current behaves differently with terminal voltages. In super threshold voltage regime, the current behaves as a square law or a linear relationship with respect to terminal voltages, gate to source, body to and drain to source voltages, whereas in the near threshold or sub threshold voltage regime, the current behaves as a exponentially, it changes exponentially with gate to source and drain to source voltages. For example, in the standard cell library used in this paper, they find that to balance the output transition times in super threshold voltage regime, they have a ratio of P n ratio Wp by Wn of 2.7, whereas to balance the standard cell library, to balance the output transition times in an inverter in near threshold voltage regime, say the threshold voltage is 0.4 volts, they are operating at a VDD of 0.4 volt itself, suppose. So, in that case they are finding that the transition times are matched if Wp by Wn is 0.8. So, that is a huge difference. So, therefore, when they use this standard cell library for near threshold voltage operation, they would not be the output transition times would not be matched, and output rise time would be quite small compared to output fall time for say a step input. So, the Wp by Wn would come out to be quite different, but since all the standard cells are sized to have nearly same Wp by Wn, also the output rise and output fall transition times, though they would not be equal in near threshold voltage operation, they would fall in a ratio. So, though they are not equal, they would fall in a ratio, and how do we deal with this situation, we will discuss as we go ahead, as we go further. Now, first let us use back of the envelope calculations to calculate logical efforts of these gates. So, let us first generalize. Say that the standard cell library is sized with Wp by Wn of S, okay, and you use a common standard cell library both in super threshold and near threshold voltage regime, and the size is S. S could be different from this 2.7 or from 0.8, okay, it could be an intermediate value, so that it does not skew the output transition rise and fall transition times too much. So, in that case, what is the effective? So, if your effective resistance of the transistor, now if you this is quite a simplistic argument, assigning a value of resistance to a transistor, but that is an effective resistance and which one can obtain through simulations. So, this is an equivalent kind of resistance. So, you can obtain it by extracting RC time constant. Suppose you have an inverter, you have a known capacitance CL and give a step input. So, you would have a rise at the output, take out the rise time, okay. And had this been an RC network, RST of P MOSFET, keep the same CL here. For this rise time, if you give a step input, if the voltage rises from 0 to VDD as a step, how much would be the rise time? For this rise time to be there, what is the value of RST? So, RST for the same TR which you get from simulations. So, that is the RST value that you are fixing for the transistor, RST of P. Likewise, you get RST of N, and then you will take a ratio, and that ratio they are saying it turns out to be 2.7. Okay. RST of N they are calling RST here. And now, for this generalized standard cell library, where WP by WN is S, and they are also applying a body bias to the N MOSFET, either a forward or a negative body bias, so that the transition times are matched. And for suppose this S is smaller than 2, is larger than 2.7, then you will have a output rise time which is smaller than the output fall time. Then you can apply a forward body bias to the body of the P MOSFET, all the N MOSFET. For all the N MOSFETs, you can apply a body bias and match the transition time. So, that is what they are doing here. So, when they apply that body bias, the resistance of this equivalent resistance of the N MOSFET changes to Y times RST. So, equivalent resistance of NMOS P MOSFET changes to, I am sorry, they are not applying body bias to the P MOSFET. They are applying an equal body bias to all the NMOS devices, because all the NMOS devices are shared in a substrate in a planar technology. So, they are applying equal body bias to all the NMOSFET transistors. So, that is easy from a layout point of view. Otherwise, for P MOSFETs you will have to bias each of the wells separately. So, when you apply body bias, this goes from RST to Y times RST for nominal voltage operation and Z times RST for near threshold voltage operation. And what about the P MOSFET? Okay. N MOSFET in nominal voltage, N MOSFET would have an equivalent resistance ST. P MOSFET, when WP by WN is equal to 2.7, would have resistance RST, then they would have both equal resistances. Now, when WP by WN is equal to S, when WP by WN is 1, then the equivalent resistance of P MOSFET by the same reasoning would be RST into 2.7, because the width of the P MOSFET device has reduced by 2.7 times, width of the P MOSFET device has reduced by 2.7 times. So, current is proportional to, this is because current is proportional to width of the device. So, width of the device has reduced by 2.57 times, and therefore, for the same terminal voltages the current would reduce by 2.7 times. It means equivalent resistance has increased by 2.7 times. So, for WP by WN is equal to S, the equivalent resistance of P MOSFET is this into 2.7 by S, by the same reason, because current is now proportional to, has increased by a value S. So, resistance has reduced by a value S for the same terminal voltages. So, that is why here this is the equivalent resistance is now 2.7 into RST divided by S. Likewise, for near threshold or sub threshold voltage regime, the WP by WN of 0.8 balances the resistances, then the resistance R and T near threshold of both P MOSFET and N MOSFET are equal. Now, you have a size S, means it will be 0.8 R and T by S for the P MOSFET. Okay. So, what is the value of logical effort? Now, logical effort the authors are obtaining with respect to the standard template inverter for this. It is as if what is the, so how is this logical effort now defined? While the drive strength or switching current is equal, the ratio of input capacitance of a gate to that of the reference inverter. So, this is how we can look at logical effort. So, what is the logical effort of this inverter with respect to this inverter? This is the standard template inverter. So, you are taking ratios of RC time constants, switching RC time constants in this or the authors take that. So, this is equal to RC time constant of the, so this is for output fall, okay. So, RC time constant, how much would that be? YRST into the capacitance. Capacitance is Cg into 1 plus S, because now you are assuming the gate capacitance of the P MOSFET and N MOSFET per unit width to be equal, divided by RST for the standard template inverter, this one RST into the capacitance. So, capacitance would be, if this inverter is driving a similar inverter, the capacitance seen would be 1 plus 2.7 Cg. Okay. So, now you cancel out the terms Cg gone, likewise ST is also gone. That is how you get Y into 1 plus S divided by 3.7. How about parasitic delay? So, here they are assuming that for parasitic delay, they are assuming that parasitic capacitance is equal to gate capacitance. So, what would be the parasitic capacitance here? It is equal to the gate capacitance, means Cp is therefore equal to 1.8 Cg. So, what is the RC time constant? So, RC time constant for output discharge for the parasitic capacitance would be RST, which is Z times RST into equivalent the capacitance when you are driving a similar inverter, which is 1 plus S Cg divided by RST for the inverter into 1 plus 2.7, 1 plus 0.8, I am sorry, 1 plus 0.8 Cg. This is for the denominator is for this inverter and numerator is for this inverter. So, what does this turn out to be? Cancel out these terms, then this turns out to be this value PFNT. Likewise, they have calculated other values of logical effort, and that is rise, logical effort for output rise, parasitic delay for output rise, logical effort for output fall, parasitic delay for output fall. For example, this is output rise RC time constant. So, you are driving a similar inverter. So, in that case it would come out to be 2.7 by S RST into 1 plus S Cg divided by RST into 1 plus 2.7 Cg. Cancel out the terms. So, 2.7 into 1 plus S divided by 3.7 S, that is what this turns out to be. So, similarly they calculate all these values. Now, we use this in obtaining logical effort of a path and thereby of a logic path using these asymmetric gates and using these for the delay optimization. Now, let us look at how do we use this to estimate the path delay for an inverter chain. Suppose this is driving a load capacitance C in. Let us call C in as Xi, X1 and CL as Xm. M could be the number of stages. So, but M could be odd or even. This is I equal to 1, I equal to 2, I equal to 3, I equal to M minus 1. Suppose the input is rising and you are dealing with near threshold voltage regime. Then for input rising, what is the logical effort in near threshold voltage regime? We know that G is, as we had done earlier, Z times because of the body bias. So, input is rising, so output is falling. So, Z times 1 plus S divided by 1.8. 1.8 is for the standard template inverter, the input capacitance. So, what is the delay of individual stage? Then it will be for input rising, it would be Z into 1 plus S by 1.8 times. Suppose this is the first stage, then it is X2 divided by X1. here the capacitance is x2, here it is x3 and here it is xm minus 1. So, suppose you have odd number of if you have even number of stages, then this m is odd for even number of stages, then you can write m as 2i plus 1. Okay. Likewise, for the so now we have estimated here the rise time rise delay, input rise delay of the first stage, and the first stage is seeing a rise delay. So, here you will have input rise delay, output fall delay. For this you will have input fall delay. So, d fall. So, what is that? What is the logical effort for fall for the inverter? So, output rise, input fall, output rise 0.8 divided by S into 1 plus S divided by 1.8 into x3 by x2. Okay. So, likewise you add all the terms and you get that for all the odd numbered inverters you will have input rise delay. So, for all the odd numbered inverters you have this. So, you begin from 1, okay, 2i minus 1 is 1, then 3, then 5, like that, 2i minus 1. So, for all the odd numbered inverters you have this as the delay, and for all the even numbered inverters you have this as the delay. Okay. So, this is the total delay you have obtained. Now, you use the method of logical effort, that is you equate all the terms x2i by x2i minus 1, that is equate the path effort, stage effort of all the stages and obtain the total delay. So, in this lecture we have discussed the back of the envelope calculation based in estimation of the logical effort values for inverters using asymmetric gate sizing, and also discussed inverter chain delays and how to optimize inverter chains using this modified method of logical effort for asymmetric gate sizes. Thank you.